Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in chapter 4, part of this playlist, which I'm calling Multivariate Normal Distribution. And let me jump to today's topic, where we're transforming a multivariate normal random variable to a chi-square random variable. Another buzzword topic for this is the distribution of quadratic forms. And let's let y be a multivariate normal with mean vector mu, covariance sigma. Then in the previous section, and when we covered Mahalanobis distance, we noticed that this transformation, the inverse of the square root matrix times y minus mu, and these are vectors. If we call that z, it's a standard multivariate normal. That means the mean is 0, all the variances are 1, and all the components are independent. So it says then z1, z2 through to zp are all independent. And note that a standard normal random variable squared is a chi-square with 1 degree of freedom random variable. But this is true for all j. So every component, if we square it, it's a chi-squared random variable, and they're independent. So thus, the sum of these squared independent random variables is going to be a chi-squared with p degrees of freedom. We just know that from the univariate uh, from univariate distributions. So, but the sum of the chi-squares can be thought of as the product of two vectors. But if we plug in what z is, we get this. And so that this quadratic form is distributed with a chi-squared with p degrees of freedom. Now let's look at this in R. So we load the mass library, and it's a package in R. It actually comes with your base distribution of R. You just have to load it and you get some additional functionality. And the functionality that I want is a multivariate random normal distribution. We can generate from it. So let's let n be 1000, the mean vector be 10, 5, 7, 9, and 20. The variance covariance matrix of this, I'm not going to say it. And then we just generate a multivariate normal random variable. We generate 1000 observations, mean vector, covariance matrix we called sig, and boom, we now have a data frame y that contains this multivariate random variable. Now the Mahalanobis distance, this function, creates this quadratic form. It takes y minus the mean times the inverse of the variance covariance matrix times this quadratic form. So for each observation, let's calculate the Mahalanobis distance and then store it. I'm going to call it in z.z, which stands for z transpose z. And let's look at the histogram of it. So let's just create a histogram, and I have some labels, and let's normalize it so the probability is true. And then we're going to plot on top of that the theoretical curve. It should be a chi-square with 5 degrees of freedom. And let's look at the plot. So the gray bars are the histogram of a random sample, multivariate normal random sample that's been transformed using the quadratic form or Mahalanobis distance. And this is what we observe. And the red line is the theoretical curve. The theory says it should be a chi-squared with 5 degrees of freedom. And look how close it is. That's pretty amazing, actually. Okay, well, the next topic is the marginal distribution. Oh, and as always, I will copy and paste the code into the comments so you can copy and paste it and play with it in R. Now, the marginal distribution of a multivariate normal random variable is the following. So if y is multivariate normal, then the marginal of any element of y is univariate. So if a marginal means like a subset of the original vector. So if that subset is just one variable, the jth component, then it's also a normal random variable with mean, the jth element of the mean vector mu, and it's the jj element of this covariance. So it's the jth diagonal. And so each component is normally distributed. And this is true for all p elements. And then remember, we're saying that y is multivariate normal. And then if the covariance is 0 for the j and the kth element, that says they're independent. And also if they're independent, then the covariance is 0. And this is only true for normal random variables. And so if they're independent, the covariance is 0. That's true for all variables, but the other way is not true. If the covariance is 0, then they're independent. That's only, it's true for normally random variables, but not true in general. Now, similarly, if we let any arbitrary partition of y into two subvectors as this, so we take our p by 1 vector, random vector, and just partition it into two random vectors. Now, this could be one component, or could be 2 or 3 or 4. I mean, it could be anything. Then the mean, if we partition it in a similar way, so y1 has the same number of elements as mu1. And then let's say it's a length that this is an r by 1 vector. So y1 is r by 1, mu1 is r by 1. Then this subvector, the covariance matrix, submatrix, is r by r. And then any marginal of the subset y is also multivariate normal. So y this time has r variables in it, but it's multivariate normal with mean vector mu1 and variance covariance matrix sigma 1 squared. Now, it's also true in the multivariate setting if the covariances are 0, so the covariance is between vector 1 and vector 2, that says the vectors y1 and y2 are independent, and vice versa. It's an if and only if. Now, let's look at our illustration here. So we load the mass library, and that's so we can get a multivariate normal random variable. So we're going to take a sample size of 1,000, have this mean vector, this covariance matrix, and we generate a sample of multivariate data, store it in y. Now what we're going to do is take the first variable, so that's column 1, look at a histogram of it, store the information in H1, histogram 1. Take the second column of y, our data matrix, which is the second variable in this 5-variate multivariate normal sample data. We call that H2. Now, top is a way to get bounds on the histograms when we plot it. That'll make sense in a second. But this KDE2 it's a two-dimensional histogram. Now notice we plotted a one-dimensional histogram and it looked just like a chi-square distribution. But how do you plot a two-dimensional distribution? Well, this KDE2D, and that's in the mass package. Then we create a layout, a special layout. And I'm not going to really go over this much, but I will copy and paste the code. But the plot is pretty cool. And this is it. So notice that, so this is y1. If we look at just a histogram of y1, it's normally distributed. If we look at a histogram of y2, it's normally distributed. And then if we look at the two-dimensional histogram, now the darker the color, the higher the peak. So you can see that it's a bivariate normal distribution. And since it's smushed, in a sense, that means a correlation between y1 and y2 is pretty high. And theoretically should be about 0.8. And so that is pretty high. And I guess what I'm showing you here is that we took a marginal of y1 and y2 and looked at the distribution, and it is bivariate normal like. And if we also look at just the marginal of y2, it's normal, and the marginal of y1, it's normal. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.